The tremendous blast is a thought that has framed how we could decipher the universe, outlining the supporting of current cosmology according to Einstein's speculation, additionally known as coarse-reading cosmology. The immense blast was the second the universe began its development, indicating the creation of all matter, energy, and presence. This occasion happened generally 13.8 billion years ago and prompted the colossal universe we notice today. However, late improvements in cosmology suggest that the colossal blast most likely wasn't the absolute beginning. Rather, there might have been a stage before the gigantic explosion that was comparably critical in shaping the universe as far as we might be concerned. This pre-period is known as incalculable expansion. Development is quite possibly one of the most interesting pieces of present-day cosmology. It suggests that before the hot, thick time of the enormous blast, the universe went through an unbelievably quick emotional development. During this period, the universe was duplicating in size at a shocking rate. To precisely represent how outrageous this extension was, assuming the universe began smaller than an atom, it would have extended to be incomprehensibly bigger than the entire discernible universe within a minuscule part of a second, around 1/4,000,000th of a second. This extension stage didn't last long, yet it assumed a critical part in forming the universe. When the inflationary stage completed, the energy driving this extension was released into space, warming it up and making the particles of matter that make up all that we find in the universe. In numerous ways, development is the forerunner to what we consider the immense blast. While the hypothesis of extension is generally accepted in cosmology today, numerous unanswered questions remain. For instance, we don't yet understand what started development, what made it stop, or how long it endured. These are open inquiries in cosmology, and noting them is significant for a deeper comprehension of the starting point of the universe. Before development, the universe was in a staggeringly thick, small place of matter, often referred to as a peculiarity. From this peculiarity, development began and eventually led to the arrangement of atoms, particles, stars, and worlds. The possibility of the colossal blast as the start of everything is engaging, but present-day cosmology proposes a more complicated picture. Some speculations suggest that the universe went through a phase before the gigantic blast. During this stage, extension made the universe develop at an incredible rate, expanding in size by basically a factor of 1,000,000,000,000 in a fraction of a second. This quick extension was fueled by a bizarre structure of energy that penetrated void space. At the point when extension completed, the energy that had driven this development was changed over into particles, warming the universe and prompting the hot, thick state we call the gigantic blast. This inflationary stage was cold and void, but it set the stage for the production of matter and the universe we see today. One of the more theoretical thoughts in present-day cosmology is the idea of timeless expansion. This hypothesis proposes that expansion didn't shut down at the same time. Rather, it halted in patches, creating a wide range of pockets, each of which could be a universe in its own right. Our universe would be only one of these patches. According to everlasting expansion, there could be a limitless number of these universes, each with its own arrangement of actual regulations and constants. This is where the possibility of the multiverse becomes an integral factor. The idea that our universe might be one of numerous, or even an endless number of universes, if this thought ends up being correct, would make sense of why our universe is so finely tuned for life. In this multiverse situation, each conceivable mix of actual regulations could exist in various universes, and we end up living in one where conditions are perfect for stars to shape and for carbon, oxygen, and different components fundamental for life to exist. While hypotheses like everlasting expansion and the multiverse remain speculative, the possibility of expansion itself is grounded in observational proof. The most grounded support for expansion comes from the inestimable microwave background radiation, CMB, the most seasoned light in the universe. The CMB was transmitted about 380,000 years after the tremendous blast, when the universe cooled enough for atoms to shape. By then, the universe became straightforward, and this light has been traveling through space from that point forward. By concentrating on the CMB, cosmologists can essentially take a baby picture of the universe. The light gives pieces of information about the universe's earliest days, helping researchers comprehend what happened soon after the immense blast and offering support for the inflationary model. One of the most significant disclosures came from the European Space Agency's Planck satellite, which took detailed pictures of the CMB. These pictures reveal unpretentious varieties in the temperature of the early universe, and these varieties match the predictions made by inflationary theory. This trial evidence fortifies that expansion isn't simply a hypothetical theory but a significant piece of how we grasp the universe's starting points. Figuring out the tremendous blast and what went before it requires bringing together two of the main hypotheses in present-day physical science: Einstein's hypothesis of general relativity and quantum hypothesis. General relativity describes the enormous scale design of the universe, including the conduct of universes, stars, and planets, while quantum hypothesis describes the conduct of particles on the smallest scales. To answer the major inquiries in cosmology, such as what the universe is made of and where it came from, researchers should develop a hypothesis that joins these two frameworks. This would permit us to comprehend not just the colossal blast, but also all the conditions that prompted it. One of the most shocking parts of the universe is its size. The most far-off objects we can notice are around 47 billion light-years away, meaning the noticeable universe is around 94 billion light-years across. This might appear to be abnormal, given that the universe is just 13.8 billion years old. How might the noticeable universe be bigger than the time it would take light to traverse it in the age of the universe? The response lies in the reality that the universe has been growing over time. As the universe grows, the distance between objects increments, making far-off objects farther away than the time it would take light to contact us. Most researchers accept that the universe stretches out a long way past the discernible universe. In truth, it's conceivable that the whole universe is boundless in size. The detectable universe is basically the part we can see, restricted by how much time light has needed to travel since the tremendous blast. There might be huge areas of the universe that we will always be unable to see. While it's conceivable the universe is boundless, the inquiry remains: is there anything past the universe? Most researchers feel a little uncertain about this thought. On the off chance that the universe is endless, there is no outside to it. The universe would basically proceed with perpetually. Regardless of whether the universe is limited, it probably won't make sense to talk about anything past it. Past would infer something beyond space, which itself is a property of the universe. So the possibility of past the universe probably won't have any physical meaning. Similarly, as the start of the universe is a subject of incredible concentrate, so too is its inevitable end. The best current gauge is that the universe will keep extending perpetually. This is expected to a strange peculiarity known as dark energy, which is causing the universe's extension to advance quickly. Before the revelation of dark energy, researchers trusted that the universe's extension would ultimately dial back due to the gravitational draw of matter. There was indeed even a likelihood that the universe could quit growing and start contracting, prompting a major crunch. However, dark energy seems to be pushing the universe apart increasingly fast. If this acceleration continues, the universe will continue to grow endlessly, ultimately arriving at a state where galaxies float so far apart that they become segregated from one another. In this situation, the universe would become cold, dull, and exhausted. Stars would wear out, worlds would float apart, and matter would ultimately rot. This is referred to as the Big Freeze or heat death of the universe. The narrative of the universe, from the enormous blast to its conceivable end, is one of the most critical and complex stories in science. While we've learned an extraordinary amount about the starting points of the universe through the hypothesis of expansion and the investigation of the vast microwave background, many inquiries remain unanswered. What caused expansion to start and end? What lies past the noticeable universe? Is there a multiverse, and if so, how many other universes exist? As researchers proceed to concentrate on the universe utilizing advanced innovation and hypotheses that bind together quantum mechanics with general relativity, we will without a doubt gain deeper insights into these mysteries. The journey to comprehend the universe is continuous, and every disclosure brings us one bit nearer to noting the extreme inquiries concerning our existence. The investigation of the universe's beginnings and structure isn't simply a logical attempt. It additionally raises philosophical inquiries about presence, reality, and our position in the universe. One significant area of interest in cosmology is the nature of dark matter, which is accepted to make up generally 27% of the universe's mass energy content. Not at all like normal matter, dark matter doesn't radiate, ingest, or reflect light, making it imperceptible and perceptible only through its gravitational consequences for noticeable matter. It is fundamental to figure out dark matter for making sense of the development and conduct of universes. Progressing studies and perceptions have given bits of knowledge into dark matter's properties, but its definite nature remains tricky. A few applicants have been proposed, including weakly interacting massive particles, WIMPs, axions, and other exotic particles. However, up until this point, no immediate proof of dark matter particles has been found. The search goes on through a mix of terrestrial trials, astrophysical perceptions, and recreations that model how dark matter impacts the enormous-scale construction of the universe. One more key area of exploration is dark energy, the secret of the power driving the sped-up extension of the universe. Dark energy contains around 68% of the universe's absolute mass energy content. Its revelation was surprising and has prompted numerous hypotheses, including the cosmological constant and dynamic fields like quintessence. Figuring out dark energy is essential, as it will decide the extreme destiny of the universe. Researchers are concentrating on its impacts on cosmic structures and attempting to decide whether it remains consistent over the long run or advances. Notwithstanding dark matter and dark energy, the investigation of huge-scale structure development offers huge experiences into the universe's set of experiences. Observations of the inestimable web, a tremendous organization of systems, bunches, and fibers, have revealed how matter bunches together, affected by gravity, prompting the perplexing designs we see today. Reproductions run on supercomputers assist specialists with understanding how these structures shaped over billions of years and continue to advance. Astrobiology, moreover, converges with cosmology as researchers try to figure out the circumstances essential for life beyond Earth. The look for exoplanets, planets circling stars outside our planetary group, has strengthened with thousands found in ongoing years. A portion of these exoplanets exists in their stars' habitable zones, where conditions might be right for fluid water to exist. By considering these far-off worlds, researchers hope to learn more about the potential for life somewhere else in the universe and the factors that make a planet cordial to life. At long last, the job of central material science in cosmology can't be exaggerated. The mission for a bound unified hypothesis that joins general relativity and quantum mechanics proceeds to challenge physicists. Speculations like string hypothesis and loop quantum gravity intend to connect these two areas, offering clarification for peculiarities like black holes and the early universe. As innovation propels, so does our capacity to notice and decipher vast peculiarities. Space telescopes like the James Webb Space Telescope are altering how we might interpret the universe by providing phenomenal detail of far-off systems and cosmic occasions. With each groundbreaking perception, we move closer to unwinding the mysteries of the universe's arrangement, advancement, and extreme destiny. The examination of the universe is a rich embroidery of logical requests and philosophical reflection. From the key powers that shape huge designs to the look for extraterrestrial life, our investigation is a demonstration of humankind's persevering, enduring interest in the universe as we endeavor to answer these significant questions. In doing so, we acquire a more profound appreciation for the immeasurability and intricacy of the universe.